Hey everybody, welcome to week 6 of PS 231. Fall is in the air. The Masked Singer is back on television. Everything is right in the world again, except for most of the details. But The Masked Singer is back, which is the only thing that I really care about. It is the greatest show in television history. I mean, don't at me. It's just true. Breaking Bad, Game of Thrones, none of them is anywhere close to The Masked Singer in terms of awesomeness. Don't even start. I don't want to hear it. So in the previous lecture, we introduced the concept of a game, and we've spent a week making sure that we knew that a game was related to some of the other stuff that we had done during the foundational weeks. And I even made a little plea for you to try to view games as ends in themselves rather than means to ends. But it turns out that most people, when they write down a game, they don't just write it down because they're trying to create an interesting story. If you wanted to write a story that mattered to somebody as an end in itself, then you would write a novel, or a short story, or a haiku, but you probably wouldn't write down a mathematical... This is what I would do instead. I'm not talented enough to write a haiku, so instead I write down games. So most people write these down not just for their inner and essential beauty, although that is a factor. They also care about what sort of predictions they can generate. And the question becomes, well, what's the machine that reads in a game and spits out a set of predictions? How do we go from games, tensions, stories? How do we get to the ending of the story? Now, we talked about that a little bit last week. So in the C block of last week's lecture, we talked about IESTS, the iterated elimination of strictly dominated strategies. And IESTS and the dominance equilibrium, two similar sides of a coin, these were intuitive and appealing tools because they relied on this intuitive and appealing concept of strict dominance, but it turned out that they didn't have a whole lot of bite. So strict dominance helped us to understand the prisoner's dilemma, which is great, and it's very important for us to understand the prisoner's dilemma. But for a whole wide multitude of games, IESTS didn't buy anything for us. So the set of predicted outcomes was precisely the same as the set of possible outcomes, which meant that if you were trying to figure out what the best course of action would be in some high-stakes relevant decision in your life, you wouldn't have any new insight. So where does the insight come from? Where do the origins of being able to whittle things down a bit? So for any given model, there may be many quote-unquote solution concepts, different ways to narrow down the set of possible outcomes to the set of predicted outcomes. That's what a solution concept is a way of turning all of the possible outcomes of a model, which you might remember is the Cartesian product of all the action sets right now. How do we whittle that giant Cartesian product down into some predictions? Well, solution concepts do that. IESTS is a solution concept. It is one out of several that one could employ. Different model plus different solution concept means different prediction, maybe. A lot of teaching you how to analyze a model is showing you the common solution concepts that somebody uses. Now, it would be very annoying if every time somebody wrote down a model, they then tailor-made some custom solution concept up. So that everything would be so custom that you wouldn't know if the unique idiosyncrasies of the predicted outcome of a given model, you wouldn't know whether to attribute those wrinkles to the model itself or to this custom tailor-made equilibrium solution concept. So instead, we have several off-the-shelf solution concepts that we use to analyze whatever game we might find. So we like to have a small set of solution concepts because that way we can use the same solution concept to analyze two different games and say, well, if I assume the same sort of behavior is happening in these two different contexts, which is to say, if I employ the same solution concept in two different games, well, that way something is the same. At least there's some ceteris being held paribus, right? That's good. Throughout the class, I'll be showing you different kinds of games now, and different off-the-shelf solution concepts that one uses to understand them. And that makes things seem a little bit just so. It makes it seem as if this is all just how it is. This is when I get really annoyed. For any given model, there are many ways to analyze it, not just the off-the-shelf ones. But in an introductory undergraduate class, you're only going to see the off-the-shelf ones. Including today's lecture, which is about the most important of all the off-the-shelf solution concepts, the concept of Nash equilibrium. But I just want you to remember that this was all the product of a lot of thinking and a lot of arguing and a lot of wonderful development over the years. So, of course, the concept of a Nash equilibrium was invented by somebody named Nash, right? No. So the concept at work in what we're going to be discussing today dates back to the early 1800s when Augustin Cournot did a study of how two firms would set a price if they were able to set a price, if they were the only two firms in a given sector. In fact, the reason that mathematician John Nash's name is associated with the equilibrium concept is not because he contributed to its substantive or theoretical aspects, but rather because he was able to prove mathematically that a Nash equilibrium always exists. So in a large class of games, this solution concept, the concept of Nash equilibrium, is guaranteed to exist. Which is good because, as we were discussing last week, we don't want to show up empty-handed when somebody says, "What are your predictions?" We want to have at least one prediction. We want to make sure that we don't rule everything out. So we don't want to leave everything on the table, but we don't want to rule everything out. How do we come up with some Aristotelian balance there? Where's the middle? What's the right amount of predictions? That's what we're going to talk about today. So I'm not going to be able to show you all of Nash equilibrium theory this week because it's going to rely on some deeper, trickier things. I'm just going to introduce the logic of Nash equilibrium a little bit today, about sort of one important sliver of it, and then we'll finish the picture in the next 2 weeks after. It's a concept, it's tricky enough that it takes a while to teach it to you, and I also think that each of the little intermediate steps is meaningful in its own right. And so I don't want to just rush to the end of the Nash equilibrium story. I want you to see how these different things come together. So today is a day where I want to introduce the basics of introductory Nash equilibrium theory and also sort of hint toward where we're headed next week. So by the end of today's lecture, my hope is that you're finally ready to come up with a reliable set of predictions if you're handed a game, which is the reason that many people write down games in the first place. Pure strategy Nash equilibrium, which is what we're going to be discussing in the most detail today, is probably the starting point for nearly every analysis that you'll come across in political science. So at minimum, anything that you see in a paper in another class that involves game theory, if it mentions an equilibrium concept that seems like it's different from Nash equilibrium, more often than not, those will just be refinements. So you'll be looking at a Nash equilibrium that also satisfies some additional properties. But the starting point of almost every prediction in game theoretic political science is the Nash equilibrium, be it refined or unrefined. So today we're going to be talking about the unrefined versions, and then as the class progresses, we'll talk about how to adjust the concept to allow for a broader set of strategic contexts. So I want to show you pure strategy Nash equilibrium from two different angles. The first is the more definitional angle. I'm just trying to make sure that you understand that we're talking about an entire profile all at once, an entire action profile, an n-tuple of pure choices that everybody made. I also want to show you a nice theoretical shortcut, a neat mathematical tool that will get you the same answers, but without having to be quite so thorough. And then finally, I want to wrap things up with a nod to the future, and we'll think about how to think about games in a probabilistic sense, which is, you're probably sad about that. Expect Utility Week wasn't very much fun. It's going to be a necessary evil for us moving forward for reasons that you'll see momentarily. So today's lecture is in 3 blocks. In the A block, I want to introduce the concept of a pure strategy Nash equilibrium in the definitional sense. So the idea of a pure strategy Nash equilibrium is that it is a strategy profile, which is to say an n-tuple of choices, one for every player, at which no player feels regret. Nobody would like to leave this profile conditional on what they just learned that everybody else did. There is no incentive to deviate. Nobody would want to unilaterally deviate in a Nash equilibrium. From a pure strategy Nash equilibrium, everybody, if they decided to change their mind after the fact, would do worse. One annoying thing about this definitional approach is it means that, if you're being very thorough, you'd have to go to every possible strategy profile and check and say, hey, does anybody have an incentive to deviate? And in introductory games, that's a perfectly reasonable way to proceed. But as the games that we study get bigger and bigger, and there are more and more players and more choices, it gets really annoying to think about every possibility and whether there's an incentive to deviate. We need some simplifying tool to help make the discovery of Nash equilibria a little bit more straightforward. So in the B block, I want to talk about that tool. That tool is called best response. We'll think about how to evaluate a given player's best response to everybody else's choices. And we'll think about Nash equilibrium as the intersection of a bunch of best response mappings. Oh, that's just exciting. You're going to be so great at dinner parties. Just remember me. I'm just asking you, just as you're sitting there eating a pig in a blanket, listening to people talk about interesting issues of the day, think of me. Enjoy your dinner party awesomeness, but remember the little people that help get you there. And then in the C block, I want to talk about what a mixed strategy is. So we'll be talking about pure strategies in the first two blocks. I don't want it to seem like when we get to next week or the week after, I don't want those to feel like they're qualitatively different. So I'm excited about the fact that today will be 2/3 pure strategy, but 1/3 mixed strategy, probabilistic strategies. Because I don't want you to get so locked into the pure strategy thing that mixed strategies become a catastrophe for you. That happens to a lot of people. So again, let's try to be abstract. Let's try to stay in third person. Let's try to be light analysts here. Let's not dig in too deep, because that's going to allow us the analytic nimbleness that it will take to really drink in the entire idea of Nash equilibrium over a few weeks. So this idea of a probabilistic strategy, a mixed strategy, plays a big role in the theory of Nash equilibrium. Not only that, it seems to comport with a wide variety of behavior in strategic contexts. It could be rock, paper, scissors, or how a baseball pitcher decides what to throw, or penalty kicks, or arms races, or all sorts of important things. But this probabilistic idea is going to play a big role in the theory, not just in the immediate next few weeks, but throughout the rest of the class. So I want to talk about what a mixed strategy is just for a whole block, so that when we get to a mixed equilibrium next week, you won't be completely unawares. So that's our goal. We want to get to the predictions. We want to turn our beautiful fables into a set of predictions. We want to be able to say to somebody, and how does the story end? How does our story today begin? Let's get started. So in the C block of last week's lecture, we talked about IESDS, or just strict dominance in general. The idea was that a strategy is bad, it's dominated, if it is so bad from a given player's perspective. What makes it so bad is the fact that the player doesn't have to think about what everybody else does. The compelling part of cutting out a column or cutting out a row is the fact that everything in that column or row was worse from a given player's perspective than another column or row. Which is to say, it wasn't even strategic at that point in time. In the prisoner's dilemma, when I know I don't want to cooperate, that's because I don't have to condition what's best for me on what you do. Defecting is best for me whether you cooperate or defect. There's no subtlety there. So it doesn't take into account the fact that a strategy profile, an action profile, an n-tuple of choices, one for every player, it doesn't take into account the fact that captures things that aren't, it's not just player by player, right? So a strategy profile, whether a strategy profile is good or bad, depends not just on each player, it depends on the mutual part. It depends on whether or not there was some extra bonus or some extra cost for the social part of the behavior. What that means is that the reason the dominance is a little bit of a weak way to analyze a game, and the reason that doesn't give you a whole lot in many games, is it doesn't fully exploit the fact that the players are interdependent. It only focuses on the part that are so straightforward that interdependence doesn't matter. What makes Nash equilibrium, which we'll be discussing for the next few weeks, such a compelling part of the story, is the fact that it accounts for all of this non-reductionist, the whole is more than the sum of its parts sort of thing. These generative factors that play into our preference structure. So the underlying logic is very simple. A strategy profile is a pure strategy Nash equilibrium if, holding everybody else fixed, no individual player would like to change their mind. Now that they know what everybody else did, they don't want to change their mind. They don't want to unilaterally deviate. There is nothing strictly better for them if they deviate. Okay? So just to get started with this, let's start with Bach or Stravinsky, which is probably the easiest starting point for this sort of thing. So one nice thing about game theory now is I can just flash this on the screen. Imagine that we're playing Bach or Stravinsky. So you'll remember the story goes that we want to go to the same concert and we don't have cell phones, so we can't text. So we want to go to the same concert, but we have different preferences over the two concerts. Okay. So the idea of Nash equilibrium is that we need to check all four of these possible outcomes. Bach, 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 Stravinsky, Stravinsky, Bach, Stravinsky, Stravinsky. We need to check all four of those outcomes and check to see from any given outcome, holding the other player fixed, does either of us have an incentive to deviate? All right? I keep saying this, but once you visualize it, it's actually hard for me to describe in words what you do because it's such a visual thing. So here's the picture, all right? Now let's start in that northwest corner. So we're in the northwest corner, we're at the Bach concert together, which gives me 1 happiness point and you 2 happiness points because you like Bach. So the idea here is that holding you fixed, you are the column player, I'm the row player. Let's hold you fixed, which means let's stay in the Bach column. So we're in the Bach column. I'm holding you fixed, which means we're staying in the Bach column. And the question is, do I have an incentive to switch from Bach to Stravinsky? Well, conditional on us being in this column, I could go to Bach, as I am right now, and get 1 happiness point. If I deviated, if I went to Stravinsky instead, I'd get 0 happiness points, which is not a profitable deviation. I don't have a profitable deviation, all right? So as of right now, conditional on you being a Bach player, I don't have a profitable deviation. Now let's think about you. Right now, you're getting 2 happiness points because you're getting to nerd out on all this counterpoint, right? You're like, Glenn Gould never sounded so good. Okay, well, you're getting 2 happiness points. Holding me fixed, leave me at the Bach concert. Do you have an incentive to deviate? Well, you'd be going from 2 to 0. So staying in my row, you're doing the best that you can do in this column. If you know that we're in the Bach row, you don't have a profitable deviation from Bach. Bach gets you 2, the deviation gets you 0. You don't have a profitable deviation. So in other words, we have 2 players, and at this profile, at the Bach profile, neither player wants to deviate. Neither has a profitable deviation holding the other person fixed. This, therefore, is a pure strategy Nash equilibrium. You'll understand why I keep saying pure strategy only after a few weeks. I just want to say it for completeness sake, so please say it with me every time, and you'll learn why momentarily. Where by momentarily, I mean in 3 weeks. If this all goes according to plan. I have no plan. You think I have a plan? There's no plan. So that's the idea there. This is a pure strategy Nash equilibrium because at it, staying in this column, there's no better row for me to find. And staying in this row, there's no better column for you to find. That's a pure strategy Nash equilibrium. So let's highlight it. On my little whiteboard that I keep notes as I go just so that I know which is the northeast and which is the northwest. So I'm going to put a little square around that and we can put, that's an equilibrium. That's an equilibrium. That's your first Nash equilibrium. That's it. This isn't that hard. What you've done up to this point is way harder. You're ready. Let's move down to the one where I'm at Stravinsky and you're at Bach. Right? So the Bach-Stravinsky profile in the southwest corner. Right now I'm getting 0 happiness points and you're getting 0 happiness points. And the question is, could either of us do better with a unilateral deviation, a 1-person deviation holding everybody else fixed, where everybody else right now is just the other player. It's only 2 players. Holding you fixed. You're at the Bach concert. You're at the Bach concert because that's where we are right now. And I'm at the Stravinsky concert. We both have 0 happiness points. If I deviated, if I went to the Bach concert, I'd get 1. I have a profitable deviation. Therefore, this is not a pure strategy Nash equilibrium. Stravinsky Bach is not a pure strategy Nash equilibrium. It is not a Nash equilibrium. This is not a prediction for us. This is not a Nash equilibrium. Why? Because at least one player has a profitable unilateral deviation. I could go to the Bach concert, see you, and get a happiness point. Likewise, you could go to the Stravinsky concert holding my Stravinsky fixed, and you could get 1 happiness point. So this is not an equilibrium. We can rule it out. Let's go up to Bach Stravinsky. Well, at Bach Stravinsky, we both have 0 happiness points. Holding you fixed, you're at Stravinsky. I could go to Stravinsky and get 2 happiness points. That seems better. So this isn't a pure strategy Nash equilibrium either. And again, you can confirm that you could deviate and go to Bach and get 2 happiness points. So that's not a prediction. That's not one of our Nash equilibria. So we can cross it out. Ding, ding. Sorry, that's not there. It's ding, ding. Finally, let's go down to Stravinsky. Right now, I'm getting 2 happiness points and you're getting 1. Well, if I deviated, conditional on you being at Stravinsky, if I deviated, I would be going from 2 happiness points to 0. That's not a profitable deviation. And conditional on me being at Stravinsky, you could defect and go to Bach, but that would just get you 0 happiness points instead of the 1 that you're getting for us being musical companions. So this is a Nash equilibrium too. This is a pure strategy Nash equilibrium. I'm going to put another square around it. So we went from 4 possible outcomes and we've reduced it down to 2. Bach, and Stravinsky. Those are the 2 pure strategy Nash equilibria for this game. Now look, there's 2 of them. This is actually a really important deal. So you can imagine what happens in a Nash equilibrium as a reasonable prediction for what would happen under, right now there's anarchy, there's nothing telling us what to do. We're just acting in our own individual best interest here in an interdependent setting. But there's 2 equilibria, Bach, and Stravinsky. There might be some compelling argument for why Bach is a more important thing than Stravinsky or vice versa, but in a coordination game like this, all that really matters is making sure that we coordinate. But there's 2 ways for us to coordinate. We could both go to Bach or we could both go to Stravinsky. How do we know which of those is going to be what happens? Well, there isn't a way for us to know. There's just multiple Nash equilibria in this model. There are multiple pure strategy Nash equilibria. That means that we have a somewhat indeterminate prediction. We can tell you that certain necessary conditions aren't satisfied, right? So Bach Stravinsky and Stravinsky Bach fail to satisfy important necessary conditions, which is to say the terms of no unilateral deviations that are profitable as laid out by Nash equilibrium. But once we have 2 equilibria, there's no reason for us to privilege one over the other in terms of our prediction, or in terms of the best way to help get at the bottom of this strategic problem. Well, to make this a little bit more vivid, let's switch this from Bach or Stravinsky to a simple coordination game, left-right, on the sides of the road on Lincoln Avenue. All right? So here's a coordination game. It has the same structure as Bach or Stravinsky, so you can confirm for yourself that there are 2 pure strategy Nash equilibria, left, and right. Because if we're on left-right, and we just crashed into one another, then after the fact, we would both say, boy, I wish that had played out differently. Which isn't what happens at one of the pure strategy Nash equilibria. And the question becomes, how do we choose between these 2 equilibria? Which one is the one that wins out? So you may have noticed that in the United States, it isn't the case that we play both of these equilibria. We only drive on the right here. So how do we know what happened? Why? Why do we drive on the right? Why do we drive on the right? You tell me. Pause the video. Think about it. Pause the video. Why do people drive on the right side of the road when it's an equilibrium for them to drive on the left side of the road? For both parties to drive on the left side of the road. Why would that be the case? How could that be an equilibrium? Did you pause it or are you just watching this? I want you to pause it. Pause it! Welcome back. So, why? Because it's the law. Oh boy. You're like, that was stupid. So why is it the law? This is actually this is important. This is really important. In a world with multiple equilibria, we need help knowing which one is going to be the one that we all agree to play. There are multiple regret-free profiles here, both on the left, both on the right. Right? Those both are regret-free. There's no regrets. Everybody's happy. So how do we know which of these to play? That's one of the roles of the state. One thing that the state does is it helps us to choose from multiple equilibria. It helps us to coordinate on our coordinated equilibrium. Because otherwise, some people would think we're playing the left-left equilibrium, and others would think that we're playing the right-right equilibrium. And that multiplicity of equilibria would itself be a problem. We need somebody to just step in and say, okay, well, let's just arbitrarily all agree to play the right-right one, as opposed to the left-left one. If there was only one equilibrium there, we wouldn't need the state to tell us. But because there's multiple equilibria, we need the state to help out and tell us which of the equilibria to play. This is a very minimal conception about what states do. They help us to choose an equilibrium which would have emerged under anarchy, but so too would others. It helps us to figure out which of the acceptable outcomes is the one that happens. You're like, that sounds really stupid. Are you just making that up? No. I'll be right back. Bookshelf of Awesomeness. There's a nice book by Harrison Wagner, War and the State. Chapter 2 of this book is Reason of State. Or if you want to be fancy, sometimes you say in French, raison d'etat. And you're like, what does this have to do with anything? This is a fancy book. This is a fancy book. This is a fancy book. This book, I'm going to read you the back blurbs. The back blurbs of books are usually not to be believed, okay? Because this is people being very praiseworthy. Okay, but this is when they're, okay. This is a fancy book. It's a very, very fancy book. What do I mean? Well, on this book, here's the back. Possibly the most important book on international relations theory since Kenneth Waltz's The Theory of International Politics, which is 1979, and probably the most important book in IR theory of the 20th century. So this is possibly the most important book on international relations theory since that. Jim Fearon said that, one of the leading IR theorists of his generation. Bob Powell, another one. This is one of the best books on IR theory I have read in a very long time. Here's an even better one. Painting on a vast canvas and tackling and integrating topics such as state formation, domestic politics, and international conflict, this book offers many brilliant insights into the nature of international relations and international... This is a fancy book. This is a very important fancy book. And it's got a coordination game in it. Where is it? There it is. Right? I mean, I'm not telling you any tales out of school here. Just keep chopping that wood. You're getting close. I mean, this was just us trying to not crash on Lincoln Avenue. It's just a coordination game. And in fact, a lot of Wagner's argument about what the state is and what it does is it helps us to solve coordination problems. In particular, helps us to choose from among multiple equilibria in coordination problems. So that stupid game, which you learned last week, with me and my little SUV and you and your roadster, trying to not go psh, that tells you why we have states, why the nation state is what it is, why it does what it does, what is its function. It's all in this stupid game. Let's just work through a couple more examples in 2x2 games. Okay? So here's a prisoner's dilemma. Now you have a hunch about where to start with the prisoner's dilemma because IESDS told you that defect is the only plausible outcome here. Let's see if that plays out in Nash land. Well, let's start from the cooperate. So right now we're at 3-3. This is what people think we ought to be able to do. So here we're saying, let's take that as the status quo. Let's see. Let's try and give it every chance that it has. Does anybody have a reason to deviate from cooperate? Well, conditional on you cooperating, I'm getting 3 right now. If I defected, I'd get 4. And right now we're up here, and conditional on me cooperating, you could get 4. So cooperate is not a pure strategy Nash equilibrium. That's good. Just imagine if IESDS and the Nash equilibrium concept disagreed with one another. They don't. You'll never prove that, but that's true. You could prove that if you wanted to. It's not very hard. Okay, let's go down. Let's check the you cooperated, I defected. Right now I'm getting 4 and you're getting 1. So I have no reason to deviate. 4 is the best I can do. So let's not worry about me. But right now you're getting 1. If you defected, you could get 2. Defect cooperate is not a pure strategy Nash equilibrium. What about cooperate defect? Well, right now you're getting 4, so you're happy as a clam, but I'm getting 1. If I defected, I would get 2. So that's not a pure strategy Nash equilibrium. How about defect? So right now we're at 2-2. Defect yields utility numbers 2 and 2. And if I defected, I'd switch from 2 to 1. I don't have a profitable deviation. And if you defected, you'd switch from 2 to 1. You don't have a profitable deviation. So this game has a pure strategy Nash equilibrium. It's defect, which just happens to be what we got from my ESDS too. This game has a single pure strategy Nash equilibrium, not 2. Right? So we don't need the state. If we needed the state in the prisoner's dilemma, it wouldn't be to help us to choose among equilibria. It would be to incentivize cooperation. These fables, there's a lot of power in there. If you understand the fable deeply, there's a lot in there. Here's a slightly tricky one. Let's do chicken. So, in the game of chicken, there's 2 players, you and me, and we can either go straight or swerve, be the first to swerve. Well, let's think this through item by item. So let's start in this northwest corner. This is the world where we both swerved. Hopefully that means we're done playing this stupid game. Okay, so it was 1-1. Conditional on me swerving though. Don't you wish that you had gone straight? Yeah. And look, you have an incentive. Right now you're getting 1. If you went straight, you'd get 2. Similarly, right now I'm getting 1. Conditional on you swerving, I wish I had gone straight. So if I deviated, I would get 2. I'd be the winner. I'd look so awesome. Instead, I look like half a chicken. So swerve is not a Nash equilibrium in this model. Now let's think about, let's go down 1. So let's think about the world where I went straight and you swerved. So I'm getting 2 and you're getting 0. Well, 2 is the best I can do in this game, strictly so I have no reason to deviate. If I deviated, I'd be switching down to 1. That doesn't make any sense. I'm good. Do you have an incentive to deviate? Well, right now you're the chicken. You're getting 0 points. I went straight, so I won. But it isn't true that you wish that you had gone straight, because if you knew that I was going to go straight, then you would have wished you would swerve. You're happy. This is actually a pure strategy Nash equilibrium, because if you deviated, you'd be going from 0 to -1. You don't want to deviate. Deviate, no. Okay? So that's a pure strategy Nash equilibrium. Straight swerve is a pure strategy Nash equilibrium. Similarly, swerve straight is. You won, you're happy. Do I wish I had gone straight? No, I don't wish I had gone straight. I'm happier with this than if we had crashed. I shouldn't have entered in this game. This is a stupid game. So that's a pure strategy Nash equilibrium. What about -1? What about the straight? Well, straight, we could both deviate and do better. Either of us could have swerved, and that means that we would have lost, but we'd be alive. So that isn't a pure strategy Nash equilibrium. We both have incentive to deviate. If I switched the row up, I would do better, and if you switched the column, you would do better. So this game has 2 pure strategy Nash equilibrium. Straight swerve and swerve straight. So the idea with this pure strategy Nash equilibrium concept as we have it is that everybody, we look at a whole profile and then we say, well, we're keeping everything in that profile fixed. Is there incentive to shift? all right? That's the most important logic. So I'm intentionally not showing you a voting game here. I'm going to hold the voting game for your problem set because I really want you to see that unilateral deviations, you have to think that through. But here's a hint. It is possible for there to be a profile where one person changes and the outcome doesn't. I'll repeat that hint. There are possible strategic settings like voting where one person could deviate and nothing really changed. So there couldn't be a profitable deviation because nothing would change. So let's do a formal definition. And I'm going to do it in the context of a 2-player game and then an n-player game. So for a 2-player game, we say that a strategy profile, which is to say a pair, it's an ordered pair, right? My choice and your choice, player A's choice and player B's choice. So that, it's a profile of actions. And we say that profile of actions is a pure strategy Nash equilibrium if no player has an incentive to deviate. How would we encode that? Well, let's think about this from player 1 standpoint first. So right now, at this action profile, which is an A1 and an A2, okay? So right now we have A1 and A2, and we know the utility number for that. So we have U sub 1 of A1, A2. That's the utility that they get at this candidate profile. And so what has to be true is that U sub 1 of A1, A2 is greater than or equal to U sub 1 of A prime sub 1, A sub 2, for all A sub prime 1 in the action set for player 1. Okay, let's unpack that. What that means is, right now, we have A1 and A2. And the idea is holding A2 fixed. Hold player 2's choices fixed. We're thinking about player 1 right now, so hold player 2 fixed. Notice that it's the same A2 on either side of the inequality. Okay? And so what I'm saying is, U sub 1 for playing A sub 1 against A sub 2 is greater than or equal to playing A sub 1 prime, any other A sub 1, any other action you could have chosen has to yield no higher utility. From player 1's perspective, holding player 2's choice fixed at A sub 2. So, right now, let's think about this in terms of the prisoner's dilemma. And we're at defect effect. Let's say that A sub 1 equals defect and A sub 2 equals defect. So U sub 1 of defect equals 2. Okay? And so the Nash equilibrium condition for player 1 here is that U sub 1 of cooperate against defect can't be higher, which it isn't. It only gives you 1. So player 1 doesn't have an incentive to deviate to any other action in her action set. A1 against A2 is as well as she could have hoped to do. Similarly for player 2. So U sub 2 of A sub 1, A sub 2 must be greater than or equal to U sub 2 of A sub 1, A sub prime 2. Some other alternative, some other choice that player 2 could have made. It can't be better. So holding player 1 at A sub 1, holding them fixed at defect, is this the best that player 2 could have hoped to do relative to all of her other choices living in capital A sub 2? That's just an annoying way to encode the idea that nobody has a profitable unilateral deviation. What do I mean unilateral? Everybody else the same. Only I change. Only I change. Everybody else stays the same. So that's a pure strategy Nash equilibrium for 2 players. Now for n players, if we had a large set of players, where large could be 3, or 4, or 5, or a Google, or whatever, it gets really annoying to have to think about writing everybody else's profile. So here's what I'm going to do moving forward. This is a new notational convention I'd like to show you to help simplify the concept of a Nash equilibrium with n players. So right now, if I write A is A sub 1, A sub 2, A sub 3, ... A sub n. That's the entire action profile. So that A, which is an element of the big Cartesian product thing, that list A, that contains everybody's choices in it. But notice we're talking about unilateral deviations, which means that I wish that I could write A as what I did and what everybody else did, right? I don't want to have to write out what I did what player 1 did, what player 2 did, what player 3 did, ... what the player just ahead of me in line did, what the player just behind me in line did, ... what the last player did. I just want there to be something that captures everybody else. Okay? So what I'm going to do is I'm going to say A sub I is player I's choice. That's one item, that's one element of her action set. A sub I, little a sub I, is just a choice made by player I. Now I have to think about what else everybody did. Well, the way that I'm going to say the actions taken by everybody other than player I is just going to be this A minus I. Now, what is A minus I? Well, it's A1, A2, A3, ... AI minus 1, AI plus 1, ... AN. So instead of having n choices, now I've got n minus 1 choices, where the person I've taken out is player I. So now if I write A sub I, A minus I mean the whole profile, but I'm really paying particular attention to just the ith element, the ith coordinate of this strategy profile. You'll see why I'm saying this in a second. It'll be more obvious once I use Nash equilibrium. Right now, this seems out of the blue. So let's just write out an n-player game. So I've got n players, and capital N equals 1, ... little n. So I've got little n players. Could be 2, could be 3, could be 4, could be a lot. And I've got capital A, that's the set of all action profiles for the n players. That's A1, Cartesian product A2, Cartesian product A3, Cartesian product ... Cartesian product AN. And an arbitrary element of that big Cartesian product is a strategy profile, an action profile A. A equals A, little a1, little a2, little a3, ... little an. That's an action profile. Bach, Bach. Red, red, red. So then we say that a given profile, A, is a pure strategy Nash equilibrium if, for all players I, for everybody this has to be true. For player 1 it has to be true, for player 2 it has to be true, ... For player n it has to be true. This must be true for everybody. It must be true that what? It must be true that for every player I, U sub I of A sub I, A sub minus I. So what is that right now? That is currently the utility that player I experiences at the profile that we're saying might be a Nash equilibrium. So that's the number that they're getting at this candidate profile that's an equilibrium. And what I'm saying is that utility number must be higher, greater than or equal to, U sub I of A sub I prime, A sub minus I, for every possible A sub I prime in capital A sub I, which is to say, for every possible deviation that player I could play. Switch from Bach to Stravinsky, switch from red to blue, switch from vote to not vote, whatever it is. What I'm saying here is, whatever they're getting for AI against everybody else has to be greater than or equal to whatever they would get for any other choice that they could have made against AI. We're holding the A sub minus I fixed. We're holding everybody else fixed. We're talking about unilateral deviations, not about everybody changing. I'm saying, once you knew that this was the landing spot, do you wish that you could have deviated? Okay? So that's a pure strategy Nash equilibrium in an n-player game. Nobody wants to deviate. So that's what a pure strategy Nash equilibrium is. You'll get some practice on the problem set, but it's actually pretty compelling logic. It's not that hard to think this through. Now, there's a certain behavioral assumption underneath this, right? We're saying that this is how we propose not only that individual level rationality plays out the way that we've been talking about. Now we're talking about something social. We're talking about a hypothesized behavior, not just at the individual level, but also at the social level. We're saying this is what a stable outcome among many rational agents would be. And stable is really what I want to say here. So if we live in a world where things are shifting, well, those shifts could be thought of as deviations. So we're in one world and then somebody deviates a little and now we're in a new world. and then somebody deviates a little, and then we're in another new world, and then somebody deviates a little, and then we're in another new world. But what would happen if you found a world where nobody wanted to deviate? Then that would be a stable world. The predictive aspects of Nash equilibrium are more related to the fact that we think that this is where things might land. This is a reasonable landing point. This isn't how we think that, or at least I don't anyway. I don't think that those people come out of the womb ready to do this. This isn't the sort of behavior that they necessarily engage in. But what I'm saying is, if the world ever does land somewhere, then one way that you might animate that landing somewhere is through this nobody has a unilateral deviation logic. Being in Nash equilibrium then would be a necessary condition, but not sufficient, for being a prediction for where things have come to be. There could be multiple places that we landed. We could both drive on the right or we could both drive on the left. Those are both stable points. Those are both stable. And only one played out. Why? Because it's not sufficient to know that it's a Nash equilibrium. No unilateral deviations is a necessary condition for being a plausible landing point for this process of deviations. It would depend on where you started and who were the ones to make the deviations and in what order, and that's all outside of our realm right now. But this logic is related to stability in a really interesting way. And this gets to some points that are popular in international relations, where it's like, many international relations theorists don't want to say that people are rational or that countries are rational, and that's understandable. It's a big bundle of commitments. You know that better than most by now. You don't have to be rational to behave rationally in the international world, because countries that don't engage in self-help behavior will lose. And so the idea is, at least in a lot of theories, including the aforementioned Ken Waltz theory, it's not pure rationality that happens, it's evolutionary in the sense that states come to learn what works well for them. They deviate when there's an incentive to, and they don't when they don't, and next thing you know, it looks like Nash equilibrium behavior, it looks like rational behavior, but it was actually a deep process that took you there, and it never involved an actual commitment to rationality as we've been discussing it. You know, this is all in some of the gray area, but it's an interesting thing to think about. But this is the predictive power of Nash equilibrium, is it seems like a landing point, a plausible landing point for some of this oscillatory behavior. Now, this particular definition of Nash equilibrium, which is the standard way to introduce it, really brings up that point. But it's a pain in the butt to have to check all 4, all 12, all Google strategy profiles. You don't want to have to do that every time. So how do we simplify this process of identifying pure strategy Nash equilibria? I'm going to talk about that logic through the best response correspondence in the B block. So let's go to the B block. So we were just talking about how this stability criterion, the stability animation, was a nice way to talk about Nash equilibrium, but it's not a super fast way to get through. So I want to talk to you about something called best response, the best response correspondence. And it's a lot like a choice mapping, actually. Don't worry, we won't be talking about warp, don't worry. So the idea of a best response correspondence is the following. Imagine that I was deciding how to play a particular game. Now I wanted to think through all the contingencies. I wanted to think through what would be the best thing that I could do against every possible thing that you could do. Right? So I'm a real chess master at this particular moment in time. So imagine that I'm thinking, let's just say we're playing Bach or Stravinsky. I'm thinking to myself, what's the best thing that I could do against Bach? And what's the best thing, if you played Bach, like what's the best thing that I could do in response to your Bach? And what's the best thing that I could do in response to your Stravinsky? So let's look at the game. Shoom. Suppose that I knew that you were going to play Bach. What's my best response to Bach? Well, if you were playing Bach, then I could go to Bach and get 1 happiness point, or I could go to Stravinsky and get 0. My best response to Bach is Bach. And if you were going to Stravinsky, what's my best response to Stravinsky? Well, I could go to Bach and get 0, or I go to Stravinsky and get 2. My best response to Stravinsky is Stravinsky. The way that I like to do this is, at least informally, I don't know how to look on a screen, but when I get a game, if somebody asks me to find all the pure strategy Nash equilibria of a game, what I do is, first thing I do is I think about role player, and I put a little asterisk next to whatever utility number is the highest in each column. So here, in the first column, in the Bach column, I'll put a little star next to that 1 that I could get if I chose Bach. And here in the Stravinsky column, I'll put a little star next to this 2 that I could get if I choose Stravinsky. Now let's do the same for you. So you're what is your best response to Bach? If we're in the Bach row, what's the best you could do? Well, you could go to Bach and get 2 points, or you go to Stravinsky and get 0. Well, Bach is better for you, so I'm gonna put a little star next to that 2 for you. Now similarly, here in the Stravinsky row, you could go to Bach and get 0, or Stravinsky and get 1. Your best response to Stravinsky as player 2, player 2's best response to Stravinsky, that's you, is Stravinsky. They get 1, so put a little star there. You'll notice that there are 2 cells where every number, which is to say both numbers, have a star. And they happen to be the 2 pure strategy Nash equilibria that we identified in the last block. So the idea of best response, Nash equilibrium is a state of affairs where everybody is best responding to everybody else's best responses. What do I mean by that? Let's think about Bach. If I'm playing Bach, your best response to Bach is Bach, and my best response to your best response to Bach is the Bach that I was playing in the first place. Bach is the best response to Bach, and Bach is the best response to Bach. Therefore, Bach is a Nash equilibrium. Likewise for Stravinsky. So this best response thing, that's just a lot faster. It's just a lot easier to say, well, what's the best thing that, conditional on what player 2 was doing, what's the best thing that player 1 could do, and vice versa. And then all we have to do is kind of look for an intersection, right? I don't have to evaluate everything. I just have to evaluate the best things from each player's perspective. So how do I formalize this idea? Well, so let's say that capital A sub little I, that's every possible A sub minus I. That's every possible strategy profile that doesn't include me, player I. Okay, so that's every possible thing that I've got to best respond to. That's the input of my best response function. I have to think about every combination of everybody else's choices. All right? So that's the domain of a function, or of a mapping here. You'll see why in a second. So the idea here is that I've got a rule that reads in everybody else and spits out the things that are best for me, my maximal elements conditional on that. Right? So if I knew what everybody else was doing, then I essentially have a decision problem like we had in week 2. Right? It's just a matter of me choosing the set of maximal elements from the things that are best conditional on what everybody else did. Essentially, then everybody else's choices parameterize my own choices. So those are the inputs of my best response correspondence. So you can say maybe capital B sub I of A minus I. So this is my best response correspondence. It reads in A sub minus I. It reads in everybody else's choices, and it spits out some subset of my choices. Right? It spits out some subset of my choices. And that's my best response. And the idea is that a strategy profile is a Nash equilibrium if everybody's choices lives in their best response correspondence for everybody else's choices. So I think that these best response correspondences in this introductory two-player case are really nice to visualize too. So I'm going to come up with a particular way to visualize them with a particular example just to keep this all super simple. So I'm going to put up an uninteresting game right now. Okay, so this is 2 players and each has 3 choices. The row player can go up, middle, or down. and the column player can go left, center, or right. And I'm just going to draw in some utility numbers here. This is a game. Cleverly constructed game to help drive home some of these visual intuitions of best response. So the way I'm going to do this is I'm going to take row players' choices. I'm going to put them on this vertical axis, horizontal axis. And I'm going to take column players' choices. I'm going to put them on the vertical axis. So right now, I've got up, middle, down. And I've got left, center, right. And I'm going to draw in the best responses for each player. I'll do player one, I'll do the row players' choices with little circles, and I'll do the column players' choices with little dots. So let's do row player first. We need to think about how row player would like to respond to each left. We want to know left, center, and right. Well, their best response to left is middle, right? So if they knew that they were going to go to the left, they could go to top, they could go up and get 1, they could go middle and get 2, they could go down and get 0. That's their best response. Their best response to going left is going middle. Similarly, their best response to the center choice, in the center column, the best that they could do is up. So I'm going to put a little circle there. Now this is where things get tricky. In the right column, the best response, now there's 2. In the right column, you could go up or down and wind up getting 1 point. So the best response, there's actually 2 elements in their best response correspondence now, not just 1. Okay? So either up or down against right. So now I've put 2 little circles in the drawing. Okay? Let's go through the same exercise for column player with dots instead of circles. Well, if they knew that they were in the up row, the best that they could do is go left and get 2. So we'll put a dot there. Left. We'll put a dot. Left against up. Similarly, we'll put a dot. Center against middle. And finally, we'll put a dot. Right against down. Well, you'll notice this game has 2 pure strategy Nash equilibria. We could have done that just from the asterisks. But you'll note also that those 2 equilibria wind up being the 2 parts of our little plot where the circle and the dot coincided. So this is an intersection of the best response correspondences. This is going to be a powerful tool when we get the mixed strategies, but for now I just want to get kind of started thinking about that. It's a very nice way to visualize these problems. So you can think about Nash equilibrium 2 ways. You can think about Nash equilibrium either as a stable outcome where nobody wants to deviate, or you could think about it through this mutual best response animation. And they're equivalent. They provide the same equilibrium predictions. They'll give you the same profile every time. It's just that one is a little bit easier to intuit, and one is a little bit faster to compute once you know what you're doing. So it really is just 2 views of the same vista. I mean, it's just 2 different angles of the same vista. They're Nash equilibrium either way, but there's a very nice way of computing them versus a very nice way of understanding them. So that's it for pure strategy Nash equilibrium. You're ready for your problem set this week. You can be done with the video if you want. Right, you're ready for your problem set. Go on and do your problem set if you want to. What I want to do for just a second here, it won't take very long, is I want to talk to you about what a strategy is in a game. I've said it several times, but I've been a little bit looser than I'd like for understandable reasons. And so I just want to make sure that we have a sense about what strategy means in the more general sense that will be applicable for next week. So it's time for us to go from introductory Nash. We're already ready for intermediate Nash, and that's waiting for us in the C block. So I really just wanted to say one thing here. This will be fast. So in the games that we've seen up to this point, we've said, well, just imagine that you're in one column, or imagine that you're in one row, and then put stars on one of the utility numbers, and that works well. But unfortunately, that logic can only take us so far. So in order to show you this, just to motivate it, let me show you an example of a game that introduces some wrinkles. So this is a game called Matching Pennies. So the idea of matching pennies is that you and I both toss a penny. And if it comes up heads, If they both come up heads or they both come up tails, then I get to keep both pennies. And if it's other than that, if it's one and then the other, if it's a heads, tails, or tails, heads, then you get to keep them both. So it's a zero-sum game. What do I mean by that? Well, you either win a penny, I either win a penny off of you, or you win a penny off of me. So in the heads, and tails, cells, I get 1 and you get -1. And in the heads, tails, and tails, heads, you get 1 and I get -1. So this is matching pennies. This is a well-known game. It's a very useful game for a variety of settings, none more important than what I'm about to use it for. So let's do a quick asterisk analysis of this game. So, conditional on being in the heads column, I want heads, so I'll put a star next to the 1 that I get. And conditional on being in the tails column, I want tails, so I'll put a little 1 next to the 1 that I could get if I played tails. Here in the heads row, well, you would like to go tails and get 1, so I'll put a star there. And here in the heads row, well, here in the tails row, you would like to get heads, so I'll put a star there. And you'll notice that there does not exist a cell that has 2 asterisks. Matching pennies has 0 pure strategy Nash equilibria, which is something that we said we don't want to have. We don't want to have to show up to our funding agency empty-handed in terms of the predictions. Does that mean that we're done? No. It just means we need to introduce the richer version of Nash equilibrium to be able to address models like matching pennies, games of anti-coordination. This is rock, paper, scissors. This is penalty kicks. This is pitching a baseball. This is offense and defense, where one is like a super strong army and one is a guerrilla army. There's all sorts of different anti-coordination games. This is an anti-coordination game. Why? One party wants to coordinate and the other one doesn't. You know how we all know that person that thinks that we're good friends, but we're not really? And then you show up at some party and they really want to coordinate on hanging out with you and you don't want to coordinate on hanging out with them? That's matching pennies. Just wait till you're old enough. So you're mid to late 20s and early 30s. Every summer is going to be an exercise in matching pennies because every wedding that you go to, you're going to think that you're free from the person that thinks that you're good friends, but you're not free. You're not free at all. I'm not naming any names in this video because I'm quite sure that whoever thinks that we're friends, they're going to find these videos. The next wedding I go to, they're going to say, these videos were so great. Who is that person you were talking about? Obviously it wasn't me. We're best friends, right, Rob? Okay, so the idea here with matching pennies and a lot of other games, including the ones we've studied up to this point, is that a strategy doesn't just have to be a single choice. A strategy, actually, in its richest form, in the form that John Nash studied, a strategy is something more general than just one choice. A strategy is a set of probabilities over your actions. I go up 20% of the time. I go middle 30% of the time. I go down 50% of the time. So instead of just making a single choice, I choose a probability vector. I choose a lottery over my available outcomes. I mix it up. This is called mixing. We call this mixing. So a baseball pitcher, like at the end of Choice Under Uncertainty Week, the baseball pitcher might have various pitches in their arsenal: fastball, slider, curveball, knuckleball. And they don't throw the same pitch every time. Instead, 60% of the time they throw a fastball, 10% of the time they throw a curveball, 20% of the time they throw a slider. What'd that add up to? 10% of the time they throw a knuckleball. So they choose probabilities to put. Okay? So a strategy in its richest form is a function. So a strategy in its purest form is a probability function that reads in your available alternatives and assigns each alternative a probability number. It's quite plausible to think that in moments where coordination happens or anti-coordination happens or a wide variety of settings, it's quite natural to think about probabilistic expectations about what's going to happen, right? So let's say that you and I are playing Bach or Stravinsky. Whether to go to Bach or whether to go to Stravinsky. And I don't know what you're going to do. Well, up to this point, last week in this, we've said, well, conditional on being in the row, in this column, or conditional on being in this column. Well, there's another way to see it. What's my expected utility of going to the Bach concert conditional on my probabilistic expectations about where you're going? Well, let's think about that. Let's say that I think that the probability that you're going to go to Bach is 1/2. Let's say that I think that you're going to toss a coin. I don't know. Let's say I think that you're going to toss a coin. So it's 50-50. So if I thought that your probability of going to Bach was 1/2 and therefore of going to Stravinsky was 1/2, then my expected utility of Bach, let's work that through. Well, 1/2 of the time, if I go to Bach, 1/2 of the time you went to Bach also. So we're at Bach together, we're musical companions, and I get 1/2 of 1 point. And the other half of the time, you're not there, I get 0. So my expected utility of going to Bach, if you were going to Bach half the time, is 1/2. And my expected utility of going to Stravinsky, well, half of the time you're at Bach and I'm getting 0 points, and half of the time you're at Stravinsky and I'm getting 2, which means that my expected utility of going to Stravinsky is 1. Which is to say, if I thought that you had a 50-50 chance of going to Bach or Stravinsky, the best thing that I could do is go to Stravinsky. Okay? I have expected utilities on that. I have expected utilities. I just said the expected utility of going to Bach because if I go to Bach, I don't know for sure what's going to happen. Why? Because I think that you might be mixing. Now, in Bach and Stravinsky, you might not be mixing, but if you're a baseball pitcher, if you're involved in poker, if you're some rival leader of another country, if I'm bargaining with the crazy type, there's all sorts of different things that might induce my uncertainty about what you're going to do. So I need to be able to think about expected utilities where the uncertainty is about your actions and where the utility numbers are coming from the structure of the game. So let's think about this in terms of a more general structure. So let's say that I thought that you were going to the Bach concert with probability P. And that means you're going to Stravinsky with probability 1 minus P. Okay? Well, let's think about that. So, if you're going to Bach with probability P, then my expected utility of going to the Bach concert, well, P% of the time you're there, so I get 1 times P. I get the 1 happiness point of being at Bach with you, being a musical companion, despite this prosaic rhythm structure. Right? So I get 1 happiness point, P% of the time, and I get 0 happiness points, 1 minus P%. So my expected utility of going to the Bach concert is P. As for Stravinsky, well, P% of the time, you're at Bach, I'm getting 0 happiness points. So I don't have to worry about that part. But 1 minus P, I get 2. So my expected utility for going to the Stravinsky show, if I think that you're going to Bach with probability P, my expected utility is 2 times 1 minus P, which is 2 minus 2P. Well, then you might be wondering, well, when should you go to the Bach concert? Well, I should go to the Bach concert if my expected utility of Bach is greater than or equal to my expected utility of Stravinsky. When is that? When P is greater than or equal to P minus 2P. If I work that out, then that happens when P is greater than or equal to 2/3. So in other words, if I think that you're very likely to go to Bach, which is to say more than 2/3 of the time you go to Bach, then I should go to Bach. But if I think it's unlikely that you're going to go to Bach, half of the time, whatever, I should go to the Stravinsky show. Why? Because I like Stravinsky more. That's what makes up for this point. That happiness point that gets made up through the probability. Now, think about it. A pure strategy at that point in time is just a degenerate lottery. It's a lottery where there's a probability 1 on something, right? So when I said that the best response to Bach was Bach, well, playing Bach for you is essentially playing the mixed strategy 1-0. You go Bach probability 1 and you get Stravinsky probability 0. Well, 1 is greater than 2/3, which means I should go to Bach according to this, and it was my best response from before too. Similarly, You going to Stravinsky is essentially you playing the strategy 0-1. Go to Bach 0 of the time, go to Stravinsky 100% of the time, right? Well, 0 is less than 2/3. I should go to Stravinsky. Well, that's what I was doing already up to this point. So this is just a slightly richer way of saying the same thing. So what I mean to say is pure strategies are special cases of mixed strategies. They're cases of mixed strategies where one of the probabilities is 1, and therefore all the other probabilities are 0. But once we're in that space, it's way easier for us to think about expected utility. You were like, what does expected utility have to do with any of this? Well, this is what it has to do with it, because eventually we're going to have to say, what probability should I play in response to your probabilities, and what probabilities should you play in response to my probabilities? That's where we're headed, okay? But I just wanted to make sure that you had a sense that this related back to the pure strategies, and you're ready to think. I don't want it to be the case next week when I say, well, the expected utility of Bach is P. I don't want you to be like, I don't know what P has. Like, probabilities are going to play into this. They have up to this point, just in a very boring way. But we're going to enrich that probability structure in the coming weeks. And that introduces all sorts of interesting wrinkles. So you got that to look forward to, which is nice. None of this diminishes the importance of pure strategy Nash equilibrium, though. And in fact, pure strategy Nash equilibria are what we talk about most of the time because they're just easier to talk about. But matching pennies tells us that pure strategy Nash equilibria don't always exist. We need something that always exists so that we don't have to show up to the funding agency empty-handed. Right now, if the funding agency said, tell me about matching pennies, we'd show up empty-handed. Next week, we will have something in our hand. You have that to look forward to as well. Boy, it's going to be a week just rich with anticipation. So that's what a strategy is in a game if I'm being all the way complete. We're working slowly, but it's accumulating, and I know that that's a lot of wrinkles. So I'm glad that this is it for today because I want you to pause and to think about pure strategies deeply. So today we talked about the rich structure of games and how to turn one of these rich structures into a set of predictions. And there was a lot of, it was kind of boring. Mathematically speaking, this is kind of boring, right? This isn't nearly as exciting as doodles. And you're like, well, exciting is a strong word. That's true. But this is a little bit rote. This is just a little bit, and here's how you do it. Asterisk here, best response there, circle here, dot there, Nash equilibrium. And that's fine. I know that there's something very appealing about just being taught how to do something. And here's how you do it. Now you know how. Go to the problem set. Do it. But there's more to it than that. These multiple equilibria are a really interesting and difficult thing to think about. If you have too mechanical of a view, then you won't see that this wrinkle is super interesting. So this wrinkle of multiple equilibria, like in Bach or Stravinsky, where we don't know if we wind up at Bach or Stravinsky, or in the coordination game where we don't know if we wind up on the left side of the road or the right side of the road, the left-hand side of the road or the right-hand side of the road. That indeterminacy in the predictions, that goes beyond indeterminacy in the predictions. That's actually indeterminacy in terms of what plays out. So for that reason, I'd like to conclude with a provocative thought. Suppose that you and I didn't have cell phones, and we needed to meet on campus somewhere. So we want to coordinate on finding a place on campus. Think about all the places on campus. Some of you haven't been to campus yet. I think there are some freshmen that aren't in Champaign, Urbana. There's a lot of places on campus. You probably saw them on the website or during your introductory tours or whatever. So let's say that we had to choose a time and a place on campus to meet, but we didn't have cell phones to help us facilitate that. So we get 1-1. We each get a happiness point if we coordinate, but we don't if we don't. We get 0 happiness points if we fail to coordinate. We have to choose a day and a time. Think about all the cajillions of Nash equilibria of this game. All that has to happen is we coordinate. Every situation where we're at the same place at the same time on our campus is a Nash equilibrium of this coordination game. So, in particular, if it's 3:22 in the morning and we're in my office in David Kinley Hall, I forget the number of my office already. If we're in that office at 3:23 in the morning, that's a Nash equilibrium. If we're in the 7th row of section AA at the football stadium at 2:30 in the afternoon, that's a Nash equilibrium. If we're both in the Illini Union, if we're sitting on the same couches in the front of the lobby at Illini Union at 11:12 in the morning, that's a Nash equilibrium. And that's, so think about time. Time is continuous, right? So there's an infinite number of equilibria just right there. There's an infinite number of equilibria in that game. There's an infinite number of Nash equilibria in the game Meet on Campus. Now suppose we were playing it. You're equally happy at all of these. I'm giving you one happiness point, no matter the time, no matter the place that we meet. All you want to do is see me. No accounting for taste. Right? All we want to do is coordinate. And there's an infinite number of equilibria. Where would we meet? And at what time? What would happen? I just told you there's an infinite number of plausible equilibria. But which one? Well, I can only tell you what I would do. I would choose noon. Noon would be the time. And you say, why noon? Because it sticks in your head. I could choose 1 or 2 or 3 or 4, but noon is the roundest number of the times. I don't want to meet you at midnight. Noon is the roundest number. Noon is the easiest number. I don't know. Why would you choose 12:37 in the morning? Why would you choose 7:22 at night? You wouldn't. You'd choose noon. Where would we meet? At the alma mater statue. Or at the front of the Illini Union, or somewhere very memorable. We wouldn't meet in some random corner of the computer science building. We'd meet somewhere we could remember. So how do we navigate this multiplicity of equilibria? We do that through this tool. This is like a heuristic device that people use. This is called a focal point. This was first brought up by Tom Schelling, who was a well-known economist who studied game theory. He did game theory as it pertains to international conflict, among other things. And he noticed that there were often situations with many equilibria. And he was like, well, I don't know what people are actually going to do. And he said, well, what if you and I had to meet in New York City? What time would we meet and where would we meet? And he said, I would go to Grand Central Station at noon, because that's a memorable place at a memorable time. That's a focal point. That is an equilibrium that's the same as all the other equilibria, but because of our humanness, that's naturally one of the ones that we would choose. So, along with the state, which tells us to drive on the right side of the road instead of the left, focal points help us to navigate this analytic indeterminacy of Nash equilibria multiplicity. And it raises interesting questions, like, what are some other focal points in the world? Is the status quo a focal point? So if we were trying to figure out how to draw a border between two countries, the most natural focal point would be the current one. Or maybe we would say, and we'll try to draw this along the geographic boundaries, because that's a focal point. Follow the river, or this side of the mountain is me, and that side of the mountain is you. There could be a lot of Nash equilibria, but let's keep it simple. So what I mean to say is, Nash equilibrium alone is insufficient to know what's going to happen. It provides necessary but not sufficient conditions. And there's a lot of interesting wiggle room about how to get to sufficiency. There's a lot of interesting wiggle room about, what actually happens. And actually, it's an interesting question. Ask your friends. Ask some of your friends on campus. Ask them, if we had to meet and didn't have a cell phone, what time and what place on campus would we meet? And that might depend. Maybe one of you and your friends are like Chipotle buddies, and so you'd meet at Chipotle at 6, right? Because you always go to Chipotle for dinner together. Or, it could be contextualized, but in the absence of context, you'd probably choose noon, and you'd probably choose one of the most famous landmarks on campus. But you didn't need game theory for that, did you? No, you didn't. So what use was the crazy coordination game that I introduced to try to motivate this focal point idea? Well, you wouldn't know that it was a problem unless we were talking about it in these terms to begin with. You wouldn't know it was a problem until you didn't have a phone. You didn't know it was a problem until you were looking around for your friend on campus. Then you'd say, oh my God, there's a multiplicity of things that could have happened, and I wish I had thought about this. I shouldn't have dropped PS 231. So, what I mean to say is, game theory presents solutions to problems. But oftentimes the solutions are themselves problematic. It's not unique in that regard. Think about a lot of politics. So, the American pragmatist philosophers of the late 19th and early 20th centuries sort of rejected the idea that there was an absolute good or absolute best. They kind of thought that the way that politics proceeded or the way the history proceeded, if things were going well, was problems emerged and we would develop solutions for those problems. And when the solutions themselves became problematic, we would design solutions for those new problems, and so on. There isn't a North Star in this standard Dewey or Charles Sanders Peirce version of American pragmatism. And game theory is sort of like a methodological version of that, where it can help you to solve a lot of interesting and difficult problems, but oftentimes it does a better job of raising important problems. It says to you, hey, here's a world with an infinite number of Nash equilibria, tell me which one you would do. Now, does that mean that it's a bad solution to things? No. Every potential solution to any given problem itself raises problems. There is no silver bullet anywhere ever. Problems are just sort of baked into the experience that we're all experiencing. And one thing that I really like about this thing that we're doing together, this game theory thing that we're doing together, is not that it provides such compelling solutions to such important problems, but that it provides such compelling characterizations of problems. And we can work on the solutions together, which is a mix of science, art, ethics, humanity. Thanks for watching.